Alright guys, I'm just going to go through some problems here with you as examples. Since we're not in the classroom, we can't really work these out in person, so I'm going to try to show you what they look like individually. So we are going to start with Julieta, if it will let me zoom in on it. So let's start with Julieta. She claims that an object in rotational equilibrium cannot spin. Javier disagrees and says that it can spin. Who is right? So basically, if you're in rotational equilibrium, then it means that you have no net torque. So it means that you have a net torque equal to 0, which means you have remember torque is equal to I alpha, which means alpha's got to be equal to 0. Okay, but if alpha is equal to 0, it can still be moving at a constant angular speed, constant omega, just like if you don't have an acceleration, you can still be moving at a constant velocity. Okay, so just a little bit to look at there. And then number 11, describe a situation in which the force is applied that results in 0 torque. Basically, there's two ways that you can do it. Let's say that we are applying a force. This is the axis of rotation. If I apply a force to the axis of rotation, there's no torque being provided. The torque would be 0. And if I apply a force that is parallel, it also would have no torque provided. So even though this one is acting at a radius, it's acting parallel to the radius, so it would have 0 torque provided. So number 1 is acting perpendicular, but it's acting with no radius. Number 2 is acting at a radius, but it's parallel, so you don't have any torque. Okay, so there you go, number 10 and 11. All right, we got two problems here. Number 19, a door of width of 90 centimeters is held open by a doorstop 55 centimeters from the hinge. The doorstop will exert 125 newtons of force to resist the door from closing. Rather than remove the doorstop, Jeffrey pushes on the end of the door to close it. How much force must he exert to move the door? Okay, so basically we have a part here. Basically, remember whenever you were doing like the moment that we got something to move is the moment that the force is greater than or equal to the resistant force. Same thing is going to be true here. The torque to get it to move is going to be greater than or equal to the resistant torque. And so the resistant torque is going to be the 125 newtons provided by the doorstop acting at 0.55 meters. Okay, so this is your force and this is your radius. And then basically that's going to, the moment that it begins to spin, Jeffrey, smart guy that he is, will have to be applying the same amount of force. So, the same amount of torque. So he'll be applying some force, but he's going to be applying it at 0.9 meters. And so if we solve 125 times 0.55, then divided by 0.9, we will need a force of 76.4 newtons to begin to close that door. And the reason that Jeffrey's force is less than the force the doorstop requires is because he's acting at a farther out. All right, number 20. So you have a balance that is 2 meters long with a negligible mass. The fulcrum is 0.75 from the left end. There is a 5 kilogram mass, and it gives you all the different places where they're hanging, but you can see them. Basically, we have an extra 5 kilogram weight. We want to know where it would have to be hung in order to balance this out. So first of all, to balance things out, we need a net torque equal to 0. Secondly, we need to know how far away everything is from this spot right here, the fulcrum. We need to know how far it is from the fulcrum. So let's figure this out. So we've got 0.5 meters from the edge. It's 0.75 meters to the fulcrum here. So the 5 kilogram is going to have a radius of equal to 0.25 meters. The 6 kilogram, we've got 0.75 and 0.75 accounted for. So we've got this 0.75 accounted for, this 0.75 accounted for, but we need this distance here. So that means that there is 0.5 left over. 0.75 plus 0.75 is 1.5. 1.5 minus 2 is 0.5. So the 6 kilograms, the radius is 0.5. And then finally for the 2 kilogram object, it's 0.25 from the edge, which means that it is, there is 1.25 meters left here. So if it's 0.25 meters from the edge, its radius from the fulcrum is 1 meter. So basically what I'm going to do is I'm going to, let's see, have to add these up. So the force is going to be just mass times gravity. So I'm going to do 50 times 0.25, and then that's pulling it this way. These are pulling it this way, so they're going to have to subtract them. They're on opposite sides. So minus 60 times 0.5 minus 20 times 1. And then I'm going to add in that spare 5 kilogram weight, which would be 50, mass times 10, remember, times R. And all of that has to add together to be 0. So 50 times 0.25 is 12.5 minus 30 minus 20 plus 50R is equal to 0. And I get 50R equals 37.5. And I am going to solve for this. So 37.5 divided by 50 is radius of 0.75 meters. And it's on the positive side. I define this as the positive side, so you'd have to hang it right there, right at the end. So you'd have to hang it on the end of the left side. All right. And then number 23, calculate the tension in the cable that makes a 30-degree angle as shown in the diagram above. So basically, if we want to know the tension in the cable, we got to have our torques equal to 0 for it not to be moving. So we've got one torque pulling it this way and one torque pulling it this way. The tension times the radius, or the tension, notice it has to be perpendicular, so it'd be the tension, let's see, sine the angle times the radius would be pulling it that way, and the force of gravity times the radius would be pulling it the opposite direction. Now, how did I know it was tension sine the angle? Well, you remember that it has to be the force perpendicular, and that would be this force right here if we're like doing tension. So this would be the opposite side, and sine theta is equal to opposite over hypotenuse, so T sine theta would be equal to the opposite side. That's how I got that. So then basically T sine theta is going to be equal to 250 times 2, or sorry, T sine theta, and you still have to add times the radius, so T sine theta times 2 would have to be equal to 250 times 2. Notice the 2's cancel, and so basically T would be equal to 250 divided by sine 30. So if I do 250 divided by sine 30, you get T is equal to 500 newtons. Okay? And again, I'm doing basically torque counterclockwise. It's got to be equal to torque clockwise. All right, and then lastly, number 21, for each of the following objects undergoing rotational motion, where is the axis of rotation? So for a planet that's spinning around, the axis of rotation, well, that is a terrible sphere, but the axis of rotation is the one that's just through the middle of the planet. For a planet revolving, you would have the sun and the planet, and the axis of rotation would be the sun. A pencil stood on end and falling over. Whenever you have a pencil that's stood on end and then is falling over, the axis of rotation would be at the tip of the pencil. A spinning top, the axis would be at the part of the top, for the spinning top, the axis of rotation would be a point that makes a line through the middle of the top. And then a satellite orbiting above the equator, the center of rotation would be through the center of the Earth. All right. So that is number 21. All right, moving on to the next step, we've got a lovely frog on a unicycle. If the unicycle wheel begins, if the unicycle wheel begins at rest and accelerates uniformly counterclockwise direction to an angular velocity of 15 RPMs in 6 seconds, find the angular acceleration of the wheel. First of all, let's see. If it's accelerating counterclockwise, that means that it is positive, so the acceleration should be positive. Next, we need to get everything into, we know it starts at rest, so we know omega initial, or omega naught, is 0 meters per second. Or, sorry, not meters per second, 0 radians per second. And omega final is going to be equal to 15 RPMs. That's rotations per minute, but I'm going to need to get that into radians per second. So 15 rotations per minute, I need to get it into radians per second. So first of all, one rotation is 2 pi radians, okay? And then 1 minute is 60 seconds. So I'm going to do, 2 pi times 15 would be 30 pi. So this would be 0.5 pi 0.5 pi radians per second would be my omega final. Now, you don't have to do that. You can leave it. You can actually multiply it out. I don't care. Some people like to keep the pi. They like to hang on to the pi. I personally am indifferent to whether you hang on to the pi. So if it makes you feel better, you can just do 1.57 radians per second. We're trying to find the acceleration though, so angular acceleration is equal to omega f, or omega final, minus omega initial, divided by t, and so angular acceleration would be equal to 1.57 minus 0 over, and it took 6 seconds to do this, so 1.57 divided by 6 is 0.26. Alpha is 0.26, and that's radians per second squared. Notice that this is positive. Again, it's positive because it's moving counterclockwise. All right, a compact disc player is designed to vary the disc rotational velocity so that the point being read by the laser moves at a linear velocity of 1.25 meters per second. What is the CD's rotational velocity in revolutions per second when the laser is reading information on an inner portion of the disc 0.03 meters away? So the thing to remember here is that velocity is equal to omega r. This is something we covered way back when we did circular motion. It's basically a linear to angular analog. And so we know that the linear velocity is 1.25. We're looking for omega if we know that the radius is 0.03. So I'm going to do 1.25 divided by 0.03 and get 41.6, actually 41.7 radians per second is equal to omega, but it wanted us to find the revolutions per second. So to get that, I'm going to divide it by 2 pi, because if I divide it by 2 pi, I'm putting it into revolutions. 1 revolution is equal to 2 pi radians. And so if I do 41.7 divided by 2 pi, I get 6.6 revolutions per second. All right, and then we've got a carousel. Sorry, that was the answer. Then we've got a carousel accelerates from rest to an angular velocity of 0.3 radians per second in 10 seconds. What is the angular acceleration? What is the linear acceleration for a point on the outer edge at a radius of 2.5 meters? Okay, so angular velocity, we go from rest, so omega naught is 0, and omega final is 0.3. Time is 10 seconds. And so if I wanted to calculate acceleration, angular acceleration is omega minus omega naught over t. So acceleration would be 0.3 divided by 10. 0.3 minus 0 over 10 if we're being technical. So 0.3 divided by 10 is 0.03 radians per second. to get the acceleration is equal to alpha r, just like velocity is equal to omega r. And so I would do acceleration equals 0.03 times 2.5. And if you do that, you get acceleration is equal to 0.075 meters per second squared. All right. Notice the analog here. Acceleration is equal to alpha r. Velocity is equal to omega r. Those are the tangential velocity and the tangential acceleration. Okay. Also known as the linear acceleration. This right here is not the centripetal acceleration. So it is not the centripetal acceleration. It's the linear acceleration. Okay, those are two different things. So the centripetal acceleration is what pulls you in toward the circle. The angular acceleration is basically how fast you're speeding up on the edge of the circle. Okay, and then the last one right here, a variety of masses are attached to at different points to a uniform beam and allowed to pivot. Rank the angular acceleration of the beams from largest to smallest. So basically what we're looking at here is a torque problem. Remember, torque is equal to I alpha. And let's see, we're looking at the angular acceleration of the beam. So we really are all going to, since we're looking at the angular acceleration of the beam, all of the I's are going to be the same. And so what we are going to do is figure out which one has the largest torque. So basically the force is going to be equivalent to that mass that's hanging down, because you just got to multiply it by 10. Force is equal to mass times 10. So let's figure out which one has the biggest forces, and then we're going to multiply those to figure out the radius. So what I'm going to do is, you see these little marks, I'm going to count each one of those as 1, 2, 3, and then 4. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, so let's figure out how much torque is applied here. So here we have 8 units of torque, because we've got 2 hanging at 4. 2 times 4 is 8. All right, for B, we have 6 units of torque. We've got the force of 3m, right? That's the equivalent, so 3m, and then times 2 tells us that we have 6 units of torque. Again, I'm not going all the way through it because you can just, we don't know what the actual masses are, so I can't find the actual torques. C, you've got 2 times 3 for this one, and then plus m times 4, giving us a total, or rather 1 times 4. So we end up with a total of 6 plus 4, which is 10 units of torque. And then finally we have m times 3, so 1 times 3 plus 2 times 4 gives us 3 plus 8, and we get 11 units of torque. So if I'm ranking these, I would have D, C, A, B. All right. Notice that D and C have the exact same masses hanging, but they flipped their spots, and in so doing, one D gets more torque because the two masses hanging out farther away. All right. Notice that the one that has the most mass in one spot is actually the least, provides the least angular acceleration because it has the least torque. All right. And finally, let's go through here. A carpenter cuts a piece of wood with a high-powered circular saw. The blade accelerates from rest to an angular acceleration of 14 radians per second squared to a maximum speed of 15,000 RPMs. What is the maximum speed of this saw in radians per second? So, first of all, we are going to just convert. So to convert radians per meters per second, rotations per minute to radians per second, we are going to do 15,000, and then that's rotations per minute. So I'm going to bring minutes up, divide by 60 seconds. I'm going to bring rotations down and multiply by 2 pi. So 15,000 divided by 60 times 2 pi gives us 1,500 and, I'm going to go ahead and round that, 1,571 radians per second. That's going to be the speed. So how long does it take to reach its maximum acceleration? Well, all right, so we know omega naught is 0. We know omega is 15,000 or 1571. I put 71, they put 70. And we want to find time. We know angular acceleration. So we can use omega equals omega naught plus alpha t. So 1570 equals 0 because it starts off at 0. The maximum speed is, yeah. So it starts from rest, so 0 plus 14t. And so if I divide that, 1570 divided by 14 is 112 seconds. So this is a very slow to get started saw. Number 30, how many complete rotations does this saw make while it's accelerating? All right, remember, go back to your angular kinematics page. So theta, remember, d is equal to 1/2 at squared plus v naught t. Remember that one? So theta is going to be equal to 1/2 alpha t squared plus omega naught t. So in this case, it's going to be 1/2 times 14 times 112 squared plus 0 times 112 because omega naught was 0. So I'm going to do 1/2 times 14 times 112 squared, and I'm going to get 87,808 radians that it covered, and I'm going to divide that by 2 pi to figure out how many revolutions, and it gets about 14,000 revolutions. There's some rounding going on in there, but it's about 14,000. Technically, it's 13,975, but pretty close. So that's how you do those. Again, we're trying to get used to you seeing how to get back and forth between revolutions per second and radians per second, and how to utilize these formulas that look very much like the formulas that we've done in the past. All right, last one, I guess. This is the last one. Yeah, last one. A roundabout on a playground with a moment of inertia. So it tells us what the moment of inertia is. It's 100 kilograms times meters squared. Starts at rest and is accelerated by a force of 150 newtons. So we know force is equal to 150 newtons, acting at a radius of 1 meter from its center. If this force is applied at an angle of 90 degrees, this is indicating that it is the maximum amount of torque from the line of action for a time of 0.5 seconds. What is the final rotation velocity of the roundabout? So basically, the reason they put that 90 degrees in there is so we knew that torque was acting wholeheartedly on it. Remember, torque is equal to I alpha, but it's also equal to force times radius. And so basically, I've got 100 times alpha is equal to 150 times 1. And so alpha is equal to 150 divided by 100, or 1.5 radians per second. Now, if it starts at rest, does it start at rest? Starts at rest. Okay, so it starts at rest, and so then we are going to do omega is equal to omega naught plus at, or alpha t. We now know alpha, and so what we are going to do is omega is equal to 0 plus 1.5 times 0.5 seconds, and 0.75 radians per second is equal to omega. All right, so these are just some example problems. I was trying to help you see how these formulas work and how they interact with each other, and hopefully you will take this and be able to kind of let those formulas start percolating around in your head, so that next week we can use them a little bit more in depth.